These notes are on section 4.1, Basic Probability Concepts. So statisticians make decisions using data by rejecting explanations such as chance based on very low probabilities. So if you're talking about some sort of experiment that you did and maybe somebody said, oh, that happened by chance, they could say, well, actually, there was a very low probability that that would happen, and so it definitely wasn't by chance. So these are reasons why basic probability concepts would be important. So they're going to help us with the interpretation of some of our data, or saying the statistical significance of some of our data. So some vocabulary terms to help us understand basic probability concepts. First, we have a trial, which is a single performance. Of an experiment or procedure. Next, we have an outcome, which is the result of an experiment or procedure. Then we have an event, which is any collection of results of an experiment or procedure. We have a simple event, which is an outcome or event that cannot be broken down into simpler components. And I gave you kind of a hint here that order matters, and this definition won't make any sense right now, but later on in the notes it will. And then last, we have a sample space, which is all possible results of an experiment or procedure. So for an example, we're going to consider rolling a die, and we're going to define a trial and an outcome. We're going to list examples of events, and we're going to give the sample space. So a trial would be a single roll. A single roll of the die if you're doing an experiment that has to do with the outcomes of rolling a die. You're probably not going to do it just once. You're going to do it several times. So each time you do it is called a trial. The outcome is the result of one roll. Maybe you rolled a 2, or you rolled a 5, or you rolled something like that. That would be the outcome of the trial. Events are collections of different results, collections of outcomes. And so we could say that one event would be rolling an even number. So that's multiple different outcomes, but you're talking about a collection of different outcomes, and so that's your event. We could talk about rolling a number less than 4. We could talk about rolling an odd number, rolling a number greater than or equal to 5, all sorts of different types of events you could have if you're rolling a die. And then last is the sample space, and that is just all the possible results we could have. So our sample space for a die would be rolling a 1, a 2, a 3, a 4, a 5, or a 6. So rolling any of those numbers. All right, next we're going to talk about the probability of events. So we have this notation. This means probability of event A occurring. This is the probability of event A not occurring. That's one way you can read it out loud, or you could read it as the probability of the complement of A. And we mean complement as kind of like the opposite of A or not A. But if we think about one of these as the probability of A occurring and one of them as the probability of A not occurring, then altogether this should be all of your results. It should be 100% of the data. And so these probabilities are going to have a very specific sum, which we're going to talk about here. So these are probability principles, and they're things to keep in mind. So we have the probability of an event. It's a number between 0 and 1. So it's specifically written as a decimal or a fraction. It is not written as a percent. You're not going to say the probability that something happens is 25%. You would say it's 0.25, or you would say it's 1/4. You also don't do odds. So we don't say that has a probability of 50-50 that it would happen. You would say it has a 0.5 chance of happening, or it has a 1 in 2 chance of happening, probability of happening. So no percentages, no odds. We only write these as decimals or fractions. Now, just because you're writing them as decimals doesn't mean they're not related to percentages. So if it had a 75% chance of happening, then the probability is 0.75. So those numbers are related. They just have to be written as a number between 0 and 1, which means we get decimal or fraction answers. The probability of an impossible event, an event that cannot happen, is 0. The probability of an event that has to happen, that is certain to occur, is 1. So you can think of this in terms of percentages if that helps your brain to understand it. This is a 0% chance of happening. This is a 100% chance of happening, which is why it's 1. Up here, this is kind of what I referenced before. The sum of the probability of event A occurring and the probability of event A not occurring must equal 1. It has to be 100% of the data, and so the probabilities have to add up to 1. If it's a probability of 0.75 that A is going to happen, then it would be 0.25 that it wouldn't happen. So it must equal 1. And then last, an event is considered unlikely if it has a small probability, such as 0.05 or less. And this is what we talked about as kind of like our threshold for things being statistically significant. We said 5%. And so 0.05 for the probability follows along with what we would expect. All right, so down here, which of these values can represent probabilities? Go ahead and take a moment, pause the video, and see if you can pick out which ones are appropriate for probability values and which ones would not be appropriate. So we have, of all these values, only 4 of them are appropriate. So we already knew that 0 and 1 were okay for probabilities. This was an impossible event. This is an event that is certain to occur. And then here we have a fraction 3/5. That fraction can occur. It's a value between 0 and 1. This fraction is too big. We cannot have negative decimals. That's not between 0 and 1. We cannot have percentages. 7 to 3, these are kind of like odds. 50-50 is odds. We can't have either of those. 0.135, that looks like a probability. And then 2.017 is a decimal, but it's not between 0 and 1, so that would not work. So these are the types of numbers we're going to see representing probabilities. Okay, so I wanted to include this just to be consistent in giving you guys ideas of how you might round different numbers. So there's a lot of information here, but it says to round by considering significant digits. And so significant digits are when you're looking at a decimal answer, you ignore the zeros at the beginning of the decimal and then start counting when you see the first non-zero number. So with this decimal right here, all of the decimal places are significant digits. They don't really give an example that's not. I'll explain it as we go through. I'll talk about significant digits in our answers, but they say that for rounding you should always include 3 significant digits, which might mean that you're going to include 4 digits in your answer. You might include 6 digits in your answer. It depends on the problem. So, but we're going to be looking for 3 significant digits when we do these. I am not sure if MyMathLab tells you to just do 3 significant digits. My assumption is that they're probably going to tell you what decimal place they want in the answers. So that is something to kind of check for and be aware of. Okay, so when we look at this, it says the relative frequency probability, and this is when you have outcomes that are being observed. So these are not theoretical outcomes. They're not saying, I know that a coin flip has 50% chance that you're going to land on heads and 50% chance you're going to land on tails. This is something you're actually observing. So the probability of event A occurring is the number of ways that A occurred when you actually observed the data, divided by the total number of outcomes that were observed. All right, so here's an example. In a Pew Research Center survey, randomly selected adults were asked if they have seen or been in the presence of a ghost. 366 of the respondents answered yes, and 1,637 of the respondents answered no. Based on these results, find the probability that a randomly selected adult has seen or been in the presence of a ghost. Okay, so we want to find the probability of yes, the probability that someone has been in the presence of a ghost. And so that means that, kind of using this as a formula, the number of ways that A occurred was the 366 people who said yes. The total number of outcomes observed were all the people who were talked to. So that's the 366 and the 1,637. So 2000, oh, you can't see it, 2003. So this is the probability. You could check and see if that fraction is as simple as it gets. So we have that fraction, and then we have this decimal right here. And so we're going to do 3 significant figures, and there's no zeros at the front, so I'm just going to include the first 3 decimals, 0.183. So this probability is approximately 0.183. If you like to think in terms of percentages, you could say there's an 18% chance, but when we say the probability that an adult has seen or been in the presence of a ghost, we're going to say the probability is 0.183. All right, theoretical probability is when outcomes are predicted. So not observed, just predicted. And we compute the probability by looking at the number of ways that A, or whatever event we're talking about, can occur, divided by the total number of simple events in the sample space. And this is where we're going to talk about simple events and what that means. So the example says, if a couple has 3 children, what is the probability that exactly 2 of the children are girls? So when we say simple events, we say that the order matters, that was part of the definition, then we have to think about not just the combinations that you can have. A couple could have 3 boys, they could have 3 girls, they could have 1 boy and 2 girls, 1 girl and 2 boys. Not just those different combinations, because there was only 4 of those. We have to think about it as order matters. So what if they have a boy first and then a girl and then a girl? What if they have a girl and then a boy and then a girl? What if they have a girl and then a girl and then a boy? There's more combinations, so there's more ways to break it down if we think about the order and the order mattering. And so that's what it means by simple events. All right, so we're going to make a list of the total number of simple events in the sample space so we know that what all the possible combinations are. So if the couple has 3 children, they could have 3 boys in a row, boy, boy, boy. They could have 2 boys and then a girl. They could have a boy and then a girl and then a boy. Or they could have a boy and then a girl and then a girl. Those are all the possibilities if they had a boy first. It's also possible that they had girls first. So they could have had 3 girls. They could have had a girl and then a girl and then a boy. They could have had a girl and then a boy and then a girl. They could have had a girl and then a boy and then a boy. And so that represents all the options of what could have happened if they had a girl first. So what is the probability that exactly 2 of the children are girls? So we're going to say probability of 2 girls would be the scenarios that give us 2 girls divided by the total number of combos. So we can kind of understand where this comes from. So let's see. This one gave us 2 girls, 2 girls, 2 girls. And if you look at these results, they kind of make sense. So the 2 girls could have been born first, the 2 girls could have been born last, or they could have been born first and last with the boy in the middle. Those are kind of the 3 options. So we have 3 options that would give 2 girls and 8 options total. So the probability is 3/8 or 0.375. That's the probability. If we want to think in terms of percentages, we could say it's a 38% chance. That's fine, but that's not the probability. The probability is 0.375. All right, let's look at this next problem. This definition actually. It says the law of large numbers. So the law of large numbers says that as the number of trials increases, the relative frequency probability, so that probability you get when you're observing the events, tends to approach the theoretical probability. Okay, so here's an example, flipping a coin. If we had 3 trials, we might say in those 3 trials that we had 2 heads and 1 tails. And we would say, okay, for these probabilities, then it would be a 0.667 probability of getting heads and a 0.333 probability of getting tails. And that doesn't fit our predicted probability that we know of heads and tails. We think it's 50-50, right? It's 0.5 to 0.5. But if you have 3 trials, you're not going to get a 50-50 relationship between the 2. You're going to have something like this. So having a 0.667 to 0.333, it kind of makes sense. It's not surprising with 3 trials. Now, if we did 100 trials, and of the 100 trials, we had 67 heads and 33 tails, that would be strange. That would be really weird. That would be a coin that is not equally weighted for heads and tails. There's some reason that we're getting much more heads than 50% or a probability of 0.5. Something is wrong with that coin. What we would expect to see more accurately here is maybe 48 heads and 52 tails. So this wouldn't be reasonable, but this would. Still not quite a probability of 0.5 and 0.5, not a 50-50, but closer. And then if we got even closer, if we got to 1,000 trials, then we wouldn't say 480 and 520 is what we would expect. We would expect the values to be getting closer and closer and closer as we had more and more trials to 50% and 50% for each of the results. So that's what they're saying here with the law of large numbers, is that the more trials you have, the closer to those theoretical probabilities or those predictions you should get. Now, one thing to keep in mind is that the law of large numbers applies to behavior over a large number of trials. It does not predict a specific outcome. So if I was sitting here and I'm trying to do 100 trials and I'm flipping a coin and I get 5 heads in a row, that does not mean that my next flip is more likely to be a tails. I'm not due for a tails. It's not more likely to be for a tails. I still have a 50-50 chance of getting heads or tails. It doesn't matter that I got 5 heads in a row on the previous flips. So that's something to keep in mind with the law of large numbers. All right. Here's another example. It says the table below describes the results of the drug tests for a group of job applicants. Use this information to answer the following questions. So first, find the probability of selecting someone who got a false negative test result. Who would suffer from this result? Okay, so I want to make sure I kind of understand this table. So we have kind of 4 groups of people going on here. So we have the group of people who use drugs and the group of people who don't. And of the people who use drugs, some of them got a positive test result because they used drugs, but some of them got a negative test result, even though they used drugs. It just happened to say they didn't. And then we've got a group of people who don't use drugs, and some of them got a positive test result, even though they don't. And then a lot of them got a negative test result because they don't. So that's what we're looking at here. So it says find the probability of selecting someone who got a false negative test result. A false negative would mean that it said that they did not use drugs, but they do. So we're looking at the subjects who use drugs and then the negative test results. So we're talking about 5 people. Okay, so the probability of a false negative are users with a negative test divided by the total number of people who took the test. So we need to look at all the people who tested, because if you remember, let's go back to our definition. It's the number of ways that this outcome could occur. So we have the number of ways that the outcome could occur, which is here. Somebody who uses drugs, negative test result is just these ones. And it's divided by the total number of outcomes observed. And so that's all of these. All right, so I'm going to add those up. 45, 25, 5, 480, 555. Okay, this is a great question to do significant figures on. So you could say that this is the decimal 1 over 111. That would be fine. If we do 3 sig figs on this one, we don't count the first 2 zeros. We start counting at the 9. And then we're going to count 3 decimal places from there, and it's okay if they're zeros. It doesn't matter. So I'm going to count 1, 2, 3, and this is where I'm going to cut it off. So for this particular problem, to have 3 significant figures or 3 significant digits, I have to have 5 decimal places. So I'm going to have 0.0090, and this 0 is followed by a 9, so I'm going to put 1. So here's our 3 significant digits right here. 1, 2, 3. So we only count after these 2. Okay, so a 0.00901 probability of having a false negative for all the people who took the test. Who would suffer from this result? Well, if people are getting a drug test for job applicants, there are the job applicants who are taking the test, and then there's the employers who want the results of the test. So if we have a false negative, that means we've got people using drugs, and it's not going to tell the employer that they do use the drugs. And so this is going to have the employers suffer. Depends on the job. Maybe some jobs it would be more important to have subjects not using drugs than others. But let's say maybe you're talking about a daycare center for very small children, you probably don't want subjects that are on drugs as employees. And so that would be a situation where employees would suffer. Okay, next, find the probability of selecting someone who got a false positive result. Oops. I wrote false poo. Okay, false positive. All right, so this would be non-users with a positive result. So non-users are these people with a positive result. So that's a fraction we could reduce, or we can use the decimal form. So we're going to not use this 0 when we count our significant figures, and then I'm going to count 1, 2, 3 decimal places after that. So we end up putting an answer with 4 decimal places, 0.0450. All right. The last question says, oh, sorry, I forgot to do the other part. Who would suffer from this result? A false positive would make the job applicant suffer. If you're not using drugs, but it says you are, that could keep you from getting a job. Probably would if they're testing you. So the job applicant suffers. Okay. And then the last question, is the test more accurate when identifying drug users or non-users? So we want to find the probability that the test IDs a user. Okay, so if the test IDs a user, we have to think about what that event would be. So total number of the ways can occur divided by the total number of outcomes observed. So here we're specifically talking about users. We're not talking about non-users, we're talking about users. So to ID a user, the total is going to be all of the users. Okay, so if we're IDing a user, that means that one of the users had a positive test result. So somebody who uses drugs had a positive test result. That was 45. Positive test. So this was 45. And the total number of users was 45 and 5, which is 50. So 45 out of 50. You could just reduce that fraction. That's a pretty nice fraction. Or you can use the decimal and just say 0.9. If the decimal does not have any more values, you don't have to force it to be 3 significant figures. You can just put this right here. And then it'll be like, oh yeah, okay, that was a nice number. Okay, so if we're trying to find the probability that we ID a non-user, then we want to have a negative test. And the total would be all non-users. So non-users would be 25 and 480, so that's 505, and a negative test result. That fraction would reduce as well, but I'll go ahead and use the decimal. And 3 significant figures will be just the first 3. Okay, so in this one, is the test more accurate when identifying drug users or non-users? We would say that it is more accurate in identifying non-users because these are accurate test results. So the probability that we get an accurate test result on a user is a 0.9. The probability that we get an accurate test result on a non-user, is 0.950, and so this number's higher. So this is more accurate for identifying non-users.